Welcome back. So now that we've gone through all of the nomenclature of the basic hydrocarbons, the alkanes, the alkenes, and the alkynes, today we are going to take a look at how these substances can react to form different types of products. The main thing with all of these types of reactions that will be slightly different from the regular reactions that you saw in grade 11 chemistry, like single displacement and double displacement and all those fun things, is that we won't have to balance them because these will already be balanced because essentially we're just moving around atoms and the products that we create have the exact same number of atoms as the reactants do. The only ones that you will have to balance will be these very first ones that we're going to take a look at with alkanes. So the first types of reactions, we're going to look at the alkanes. The alkanes don't go through as many reactions as the alkenes and the alkynes do. The most basic one is a combustion reaction. So all hydrocarbons can go through combustion reactions. Alkanes, alkenes, and alkynes. You'll recall combustion reactions from grade 11. And we looked at them a little bit in grade 12 as well when we did some of the thermochemistry reactions. And essentially we react the alkane or the hydrocarbon with oxygen to produce carbon dioxide and water. If not stated, the assumption we're going to make is that it is a complete combustion. If it is an incomplete combustion, that means we also produce carbon monoxide and carbon in the form of soot, as well as the normal products of carbon dioxide and water. So here we have propane. We want to write a balanced chemical equation for the complete combustion of propane. So propane, if you recall, looks something like this. So we've got 3 carbons and 8 hydrogens. This will bond with oxygen in order to produce carbon dioxide and water. And then you can go through and figure out all of the balancing for this. Okay, so that is your job to do. We would have done this a lot in grade 11, so this will just be some extra practice for you. Now, alkanes can also go through an industrial process called cracking. And essentially what cracking is it takes a very long hydrocarbon. So this one's not very long. This is only 4 carbons. But let's say we've got a hydrocarbon that is made up of hundreds of carbons long. That is very difficult to react. So what cracking does is it takes this very long hydrocarbon and it breaks it into shorter chains using a catalyst in a very high temperature. So this is what's done to take crude oil, which is the oil that we find in the ground, and refine it into usable products like gasoline and propane and gases that we use to make our cars run, to heat our homes, to cook food in a barbecue. Your catalytic converter, we've talked about this as well when we did kinetics very briefly, also takes the gasoline, which is a longer hydrocarbon, and breaks it down into smaller molecules that are much easier to go through the process of combustion. So here we've got these very long hydrocarbon chains represented by the gray circles, and then heat and a catalyst will break it down into these smaller compounds that are more usable and more combustible.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long chain molecules. The process of cracking breaks down long chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short chain hydrocarbons to meet the demand for them, as the longer chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking using high temperature and pressure, or by catalytic cracking at low temperatures and pressures but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain lengths, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking.
So the third type of reaction that can happen with an alkane is called a substitution reaction. What I want you to remember, we're going to be talking about two main types of reactions throughout this process. In a substitution reaction, we make two products. So in your notes, I want you to highlight two products. You always need two things that you're forming from this reaction. A substitution reaction is when we take a halogen and it reacts with, when we take an alkane and it reacts with a halogen. So here we have a halogen, which we see with the two green molecules. This could be fluorine, chlorine, bromine, or iodine. It doesn't really matter what it is. And essentially what happens here is the halide, which is our short form for one of those halogens, will replace a hydrogen. So I'll show you how that works with the molecules. Let me just make myself bigger. There we go. So here we have our alkane. This here is butane. It has all single bonds. And we'll call this chlorine. It doesn't really matter. So one of the hydrogens on my alkane is going to come off. And one of the halogens, that will be a chlorine atom, will come off as well. This chlorine atom will substitute with that hydrogen, and the hydrogen that came from the alkane will substitute with that halogen. So now we have two products. One of my products is called a hydrohalide. So this is a hydrohalide. This one particularly is called hydrogen chloride, or we can even call it hydrochloric acid because it's got the hydrogen and the chlorine. This, we've now created an alkane that has a substituent group on it. And we know how to name this. So because it's an alkane and it has 4 carbons, this is called butane. But we have replaced that second hydrogen, so we call this 2-chlorobutane. Now, why did it come off the second hydrogen? It doesn't matter. It could have come off either of these. If it came off of here, I would call this 1-chlorobutane. If it came off of here, it would also be called 1-chlorobutane because I have to number my carbons from the side that has the lowest number for the substituent group. And if I used this carbon instead, it would still be called 2-chlorobutane, again because of the numbering system. So in a substitution reaction, we end up with two products. An alkane, this is called a haloalkane now, or a halogenoalkane because now we have a halogen on it, and a hydrohalide. Okay, so here we can see the reaction in a little bit more detail. In order for this reaction to happen, it does need a catalyst, and the catalyst that we use is heat. Catalysts always have to be written on the arrow between the reactants and the products. So here we have our alkane. In this case, this one is called propane. There are hydrogens everywhere around here. I'm just showing the hydrogen that's being substituted, okay? And then here we have our, in this case, bromine. So the hydrogen and the bromine will substitute with each other and switch places. So when that happens, we end up with, in this case, an alkyl halide. So this is called an alkyl halide because now it's no longer an alkane because we have taken away one of those hydrogens, and a hydrohalide. So the name of this compound would be 1-bromopropane and then hydrogen bromide. Now this reaction can happen again, so I can take that 1-bromopropane and I can react it with another substitution reaction in bromine, and we can get a whole number of different types of products. So the second bromine can bond to the second carbon, so I get 1,2-dibromopropane, or it could bond to the first carbon or the third carbon, or it could bond to even the same carbon. If we have two of the same substituent groups on one carbon, you still need to indicate both positions because whatever prefix I have here, I need to have that many numbers. So because I'm saying di, I have to have two numbers even though they're the same. In all of these cases, I still have a second product, which is going to be the hydrohalide of hydrogen bromide. So here's an example. Draw an equation for the reaction of methane and chlorine. So let's do this. So we've got methane. Oh, where's my pen? Not on. There we go. Okay, so methane and chlorine. So in this case here, the chlorine can say be written this way, and I've got my hydrogen. So what will happen? The hydrogen and one of the chlorines will switch places with each other. So we are left with my carbon and my chlorine, but this time I've got a chlorine on here and a hydrogen over there. And then the rest of this molecule will be what it was before, and we've got that. So the names of my products, now I will have chloromethane and hydrogen chloride. Okay, so those are my two different products here. One thing to remember, in a substitution reaction, we always have two products. One atom is being substituted with another one. Okay, so we see that there. And you will see that I write the catalyst on the arrow to show what's happening. So I have heat here. Next, the cycloalkanes. So here, you'll notice in order to create a cycloalkane, I have to take off. Okay, so here is my alkane. I have to take off two hydrogens in order for these to bond together. Oof. There we go. And let's replace this here. So in a cycloalkane, it can again go through a substitution reaction. So in this substitution reaction, let's call this iodine. Same thing will happen. One of the hydrogens from the cyclic structure will replace with one of the halogens. So I still get two products. I still get that hydrohalide, and now I get an alkyl halide again, but this time it is in a cyclic structure. So what would I call this? This is 4 carbons, so this is butane, but it is a cyclic structure, so this is cyclobutane, And now I have this iodine here. So this is iodocyclobutane. And then here is my hydrohalide, which is hydrogen iodide. So here's another example. Here I've got 6 carbons. And again, the only reason why I'm showing these 2 hydrogens here is to show how the substitution happens. The X represents my halogen, whatever it happens to be. So one of the halogen atoms will switch places with one of the hydrogens in order to create my hydrohalide. And then we're left off with a cycloalkyl halide. So cycloalkyl, and now we have a halogen. Highlighters are your friend here again, so you can see what's happening. And just like before, the catalyst for this reaction will still be heat in this case. So here's an example. We've got cyclobutene and iodine. So my first step is to draw out what my cyclobutene would look like. So butane has 4 carbons. Let's actually do this as a ring structure. So cyclobutane and what was the other one? Cyclobutane and iodine. And so iodine we can draw like this. My products in this case with heat on my arrow will be my cycloalkyl halide and my hydrohalide. So here I now have iodocyclobutane and hydrogen iodide. The second example here goes in the opposite direction. So if I have chlorocyclopentane, this is the synthesis of chlorocyclopentane. So that means the chlorocyclopentane is my product. If that's my product, what reactants did I need? So if we're working backwards here, this is chlorocyclopentane. I want to know what cyclic structure I needed and which halogen I wanted. Obviously in this case, because we see chlorine here, I know that the chlorine will be one of my reactants, so chlorine gas, and then my cyclic structure will be the other one. So I've got cyclopentane and chlorine, which will produce the chlorocyclopentane, and don't forget, all substitution reactions have 2 products, so the hydrogen and the chlorine will come together to make the hydrogen chloride. So these are the reactions for cyclic structures. Next, we're going to take a look at alkenes and alkynes. So these ones are a little bit different because of the nature of the double bond and how the double bond will react. So I'm just going to make our cyclic structure here. Here, these are called addition reactions. So this is something that you want to highlight as well. An addition reaction, unlike a substitution, will only make one product. Okay, so essentially what's happening is the multiple bond is breaking, and then we are adding something else in those 2 open bonding sites. So here I have, let's make it bigger here. Nope, don't want to do that. Okay. So here I've got an alkene. What ends up happening here in an addition reaction is the double bond will break. And by breaking apart the double bond, I now have 2 open bonding sites. I have one here and one over here. So these open bonding sites is where the other atom or molecule will come in and join those spots. Okay, so that's why we only get one product. We're just filling in the empty gaps from when the double bond breaks apart. So atoms are added across the multiple bond, whether it's a double bond or a triple bond. We don't lose any hydrogens at all, which is why there's only one product. And we have 3 different types of reactions that could occur, which depends on what it is that we're adding around that double bond. The first one is called a halogenation reaction. So in a halogenation reaction, we are adding, quite simply, a halogen. Okay, so here is a halogen. And the halogen could be fluorine, chlorine, bromine, or iodine, doesn't matter what it is. Again, we have a catalyst. The catalyst for this reaction is either heat or ultraviolet light. Okay, so either of those will cause that to work. So I'll show you how this works with my molecules. So here is our alkane. We're going to break apart the multiple bond, and we are going to break apart our halogen, and one of those halogen molecules will go into the open site, and the other one will go here. Okay, so now I've created my one product. The name of this product, let's say this was chlorine, this would end up being 1,2-dichloro, and my parent chain has 4 carbons, so 1,2-dichlorobutane. Okay, so I started off with butene, but now I have butane. So what this tells me is that in an addition reaction, we are essentially going from an alkene into an alkane. I'm not sure if I had this up on the last time, so just in case, so you can see what that is there. So our first one is a halogenation, and here we have another example. This is ethene. So with ethene, the double bond will break. Okay, so this bond will break, and then when it breaks, we have an open bonding site on each carbon because carbon needs 4 bonds. So before it had 4 bonds with the double bond, but now that we break it, each carbon needs 1 more. So that halogen will bond itself in both of those open bonding sites. Does it matter if I write the 2 halogens on the top or both on the bottom or opposite? Absolutely not. Okay, as long as they are surrounding where the double bond was. With 2 carbons, that's irrelevant, but when I have 4 carbons, if this is where the original double bond was, I can't add the halogens over here or over here. Okay, they have to be surrounding the atoms that originally had the double bond. So here, what are we making? This again is called an alkyl halide because it's an alkane now that has halogens on it. I would call this 1,2-diiodoethane. That would be the name of my product. Okay, so one product going from an alkene to an alkane. Now, if you recall, when we were talking originally about alkanes and alkenes, I showed you a little video that gave you a test to identify whether or not something was an alkane or an alkene. This is the reaction that I was talking about. So the bromine, if it was right here, the bromine is that reddish orangey liquid. When you break apart the double bond, this bromine also breaks apart in order to come into these open bonding sites, which is why the color goes from red to colorless, because now there's no more bromine at all. It's all been used up, and it's now in this alkane. So a reaction mechanism is something that we will specifically take a look at for these addition reactions of the halogenation. So a reaction mechanism shows exactly what's happening within each step of this particular process. Alkanes will react with halogens in actually more detailed steps than what I just showed you overall. This is known as a free radical substitution reaction. So a free radical substitution is when we have one atom that's being replaced by another one. So essentially that's what's happening here. We've got a hydrogen that's being replaced by something else. This is specifically for the alkane reactions, not the alkene reactions, because alkenes go through additions. So this is for the alkanes. And a free radical is any atom or group of atoms that have an unpaired electron, one single unpaired electron. And the reason why that happens is because when you break apart a bond, so this was our original alkane. So when this was our halogen here from the substitution reactions. So when I have this substitution reaction, when this atom comes out, I now have one pair of electrons that is right here that is no longer bonded to anything. So that's called a free radical. And when this breaks apart, in order to switch places, this also has a single unpaired electron that is waiting for something else to bond to it. So these two molecules are now called free radicals. So there are three stages to this substitution reaction in detail, and we're going to go through each of them. First of all, this is known as a homolytic fission. So homo, whenever you see that word, means the same, and fission means to break apart. So when a chemical bond breaks, each atom gets an electron. So here, when I took off that hydrogen, the carbon has one of those electrons, and the hydrogen has the other one. Okay, here when I broke apart this halogen has one of those electrons, and this one also has one electron. So those are my free radicals. So here I've got chlorine. Chlorine can be broken apart using UV light. So now I have two free radicals that each have a single unpaired electron. When I put these together, these two unpaired electrons come together to create that shared pair, which is our bond. A heterolytic fission is when you create these free radicals, but you have two different products. So here, I've got the same thing. I've got two chlorine atoms that are exactly the same. When I break apart some types of things, I end up getting ions. So in a heterolytic fission, one atom receives both electrons. So here I've got hydrochloric acid or hydrogen chloride. When these break apart, we've got hydrogen, which has lost an electron, and chlorine, which has gained an electron. So here I have the creation of a cation, which is positively charged, and an anion, which is negatively charged. So now let's go through the reaction process. This here is the general substitution reaction between methane and chlorine. So methane is right here, and then this is my chlorine. Okay, so this is the reaction that we're going to go through. The chlorine will break apart, the methane will lose its hydrogen, and then we end up forming the chloromethane and hydrogen chloride. So the first step is called initiation. In initiation, this is where we have to create these free radicals. So this is where we have a homolytic fission of chlorine that produces, oops, I'm losing stuff here. I'm back. This produces two free radicals. Okay, so we've already seen this here. The UV light breaks this apart. I've got a free radical with a single unpaired electron for each chlorine. Next, we have propagation. So in the propagation, this is a multi-step process depending on what's happening. The first thing is there's a reaction between methane and one of my chlorine free radicals. So what happens here is the bond between methane and one of these hydrogens is going to break apart. Okay, and what I'm left with is this methyl free radical that has nothing happening yet. But the one that came off, the hydrogen that came off is now going to bond to one of the chlorine free radicals, and now we've created a compound. So we've got a methyl free radical, we have a chlorine free radical that's still hanging out, and now we have hydrogen chloride. So that's my first step. My second step is where this methyl radical is now going to react with the chlorine free radical in order to make this chloromethane. Okay, so essentially what's happening here is another chlorine molecule has to break apart in order for this to happen. So another chlorine molecule breaks apart. So I've now made this chloromethane molecule, and now I have another chlorine free radical. And then this process will continue on and on and on until I get to my termination step. So in a termination step, I want to make sure that I don't have any more radicals that are left over. So when the concentration of this hydrocarbon decreases, so remember, we're not just talking about one molecule, we're talking about millions of molecules. When we run out of this hydrocarbon, we're not going to be creating or using up as many of these free radicals. So eventually the reaction will stop. Okay, so here are the three reactions that are essentially happening. The chlorine is breaking apart to create chlorine radicals, and then any extra radicals that are left over are going to come together. So if I had 2 chlorine free radicals, but I no longer have any more of the methane for it to bond to, then these extra free radicals will bond together to create chlorine. If I have any methyl groups, any free radical methyl groups like this, they can bond together, and now I will create, instead of methyl, I will create ethane. Okay, so 2 of these would bond together. And if I still have some extras, I might have some free radical methyl groups and also free radical chlorines. This would be the final molecule that would be put together that tells me now my reaction is over because I have no more free radicals left. So that is the detailed process of how a substitution reaction happens. Now going back to the alkenes, where we've got our double bonds, let me go back and remake this. So our first type of addition reaction was the halogenation reaction, where we added a halogen. The second type of addition reaction is called a hydrogenation. In a hydrogenation, what we're doing is we are taking hydrogens and we are adding them here. Again, because this is an addition reaction, I'm only going to be making one product. So let's show you what that looks like with the molecules. So here I've got, again, butene. I've got my double bond, I've got 4 carbons, and I have a hydrogen. So just like in the first one with the halogenation, I'm going to break apart the double bond. When I break apart the double bond, I now have 2 open bonding sites. Here's my hydrogen. The hydrogen is going to break apart as well, and it's going to bond in those open bonding sites. What have I created now? Again, I have created an alkane because I only have single bonds, and I've gone from butene, and now this is butane. Okay, so this process, hydrogenation, I talked briefly about when we were looking at the saturated versus unsaturated hydrocarbons, and I talked a little bit about butter and oil and which one is healthier for you. Essentially, when they're making margarine, this is the process that they're going into. They're going through a process of hydrogenation where they're breaking apart double bonds within healthy unsaturated fats, and instead they are saturating it with hydrogen, and what this does is it turns it into a solid, which makes margarine spreadable. The catalyst in this reaction is pressure, so that's what we would write on the arrow. Here I have propene, and propene will react with hydrogen. The double bond between the propene, so maybe with your highlighter, I want you to highlight the double bond here. That will break apart, and we will be left with 2 open bonding sites on the carbons that are surrounding where the double bond was. It's not going to be here because there was no double bond here. Okay, and now we've got the 2 hydrogens that are on either side of the double bond. I've gone from an alkene into an alkane. Okay, the next one is called a hydrohalogenation. So based on the name, hopefully you can figure out what we're adding here. In a hydrohalogenation, we are going to add a hydrohalide. Okay, so hydrogen and either fluorine, chlorine, bromine, or iodine. For this reaction, the same thing is going to happen. So the double bond will break apart, and when we break apart the double bond, the hydrohalide will also break apart, and then the other atoms will go into those empty bonding sites. Okay, so here now I've got my halogen. Let's say this is chlorine. This is now called chlorobutane. I'm still going from an alkene into an alkane. So here the catalyst is either UV light or heat. And products that I'm making, I'm breaking apart the double bond. In this case, you'll notice that I had put the halogen on the first carbon. If that's the case, then I would get one bromopropane. But I could have just as easily had the halogen on the second carbon and a hydrogen on the first one. So I could also make two bromopropane in this case. Now, how do you know which product is made most often? As you recall, there are millions of molecules that are going through this reaction, not just a single one. One of these products is actually more common than the other. And this has to do with something called Markovnikov's rule, which we are going to look at after we finish the last class of reactions here. The last one is called a hydration. So in a hydration, we are again starting with a alkene. So we've got our double bond, but this time we are going to react it with water. So in this case, oops, you didn't see, I don't think I made myself smaller there. So here we've got our alkene again and water. So again, the double bond will break apart. There we go. And I have two open bonding sites, so my water molecule also has to break apart. The water molecule is going to break apart into hydrogen and hydroxide. So remember when we were looking at the equilibrium unit, these are the two ions that it breaks up into. So one of those will go in one of the open bonding sites and the other will go in the other open bonding site. So here, this is what I've created. This is actually called an alcohol. And when we get into functional groups, we're going to learn how to name these. But an alcohol is anything that has this hydroxyl group attached to it. This is actually called butanol. So butanol, all is the ending that we use for alcohols, and we attach that to the name of the alkane. So this is butane. Butane, we take off the E and add OL to become butanol. We're going to look at alcohols in a lot more detail when we get to the functional groups, but that's what this is called right here. I think that I didn't make my screen smaller when we were doing this, so I'll just show this to you again. Okay, so the two different products, depending on where the bromine is bonded, can either be on the first carbon, so that was this carbon here, or it could be on the second carbon. And so it could have been here as well. And they could have both been at the top. It doesn't have to be one at the top and one at the bottom. That's kind of irrelevant. The one important thing is that the two atoms have to be on the carbons that were attached to the double bond. Okay, so here is the last one. So a hydration is the addition of water. Again, our catalyst could be UV light, heat, or sulfuric acid. That can also be a catalyst here. So here I have ethene. The double bond between the two carbons will break. I'm adding water here. And when the double bond breaks, I have an open bonding site on each carbon. So the hydrogen and the hydroxyl group will bond there. This creates a compound called an alcohol. And you'll notice the ending for this. So this is an alkane now because we only have single bonds. We take the alkane ending of E and just replace it with OL. We will be going over this in more detail when we get to that. So here's an example. Write the equation of 1-butene and hydrobromic acid. So 1-butene and hydrobromic acid. 1-butene plus hydrobromic acid. Whenever you are doing any kind of organic reaction, you have to draw it out. So first of all, butene has 4 carbons, and my double bond, because it's an alkene, is at carbon number 1. So I need to draw in the rest of my hydrogens. Don't forget to count everything up to make sure that all of your carbons have 4 bonds. And then I have my HBr. So in this case here, the double bond breaks apart. And when it breaks apart, it creates an open bonding site on the carbons surrounding that. So my product still has 4 carbons, but now we've got an open bonding site here and here. So what will go there? This hydrogen bromide will break apart, and the hydrogen and the bromine will go on each one of the open bonding sites. So what have I created here? This is now carbon number 2, because I'm going to start numbering from this side. So this is called 2-bromobutane. Okay. In an addition reaction, we only have one product. That's it. Okay, so that's my only product. Now, the other thing that could have happened is I could have instead had the bromine here and the hydrogen there. If that's the case, the name of this would be 1-bromobutane. Either of those products is possible, but I did mention something called Markovnikov's rule, which will tell us which product is the more common one. Okay, so here's 1-butene. I can create 1-bromobutane or 2-bromobutane. Which one is the more common product? We base this off of something called Markovnikov's rule. So why is it called Markovnikov's rule? He was a scientist that came up with all of this. And essentially what he said is the rich get richer. What does that mean? If you have a hydrohalide, and so let's make this over again. So here we have an alkene, and if you are adding water or a hydrohalide, so we talked about 4 different reactions. We did one where you were adding, let's see here. So the first reaction was a halogenation, where you added a halogen. When I break apart the double bond, because these are both the same, you're going to get the same answer regardless. It's going to be 1,2-dichlorobutane. Okay? If I was going through a hydrogenation, where I'm adding hydrogen, when I break apart the double bond, I'm going from butene to butane because these are both the same. The only time that Markovnikov's rule applies is when we are working with either a hydration reaction, where we're reacting with water, or a hydrohalogenation reaction. So, okay, when I break this bond apart, you'll notice that the 2 carbons of interest here have different numbers of hydrogens. So the carbon on the end has 2 hydrogens attached to it. The carbon that's in the middle has only 1 hydrogen attached to it because it's bonded to 2 other carbons. When you have, for example, a hydrohalide, Markovnikov's rule says that the rich get richer. What this means is this carbon here that already has 2 hydrogens is going to be more likely to get the hydrogen. So that hydrogen will bond to the open bonding site of the carbon that already has more hydrogens, which means that the halogen will go to the other carbon. The same thing happens with water. Okay, so when water splits apart, I've got these 2 open bonding sites now. When water splits apart, the hydrogen ion from the water will go to the carbon that already has more hydrogens on it, which is right here on the end, and the hydroxyl group will go on the other carbon. So these are called the major products. We can make other ones, but these are the major products, the ones that are found more often based on Markovnikov's rule. So when a hydrohalide or water is added to an alkene or an alkyne, the carbon with the most hydrogens gets the other hydrogen. So here's an example. I've got 2-methyl, 1-pentene, and water. I need to identify the major product. So 2-methyl, 1-pentene. Let's draw this out. 2-methyl, 1-pentene plus water. So we need to figure out what's happening here. First of all, this is an addition reaction because we've got an alkene. So let's draw out this substance. So pentene has 5 carbons, 3, 4, 5. The double bond is on carbon number 1. And on carbon number 2, I have a methyl group. So there's my methyl group. And now don't forget all of your other hydrogens. This carbon only has 2 things bonded to it, so it needs 2. This carbon already has 4, so this carbon is good. This carbon needs 2, and my last carbon needs 3. So here I've got my water. My water is going to split apart into hydrogen and hydroxyl, and my double bond is going to break apart here as well. When my double bond breaks apart, I have an open bonding site on each of the carbons surrounding that double bond. So the hydrogen is going to go on the open bonding site of the carbon that has the most hydrogens. This carbon already has 2 hydrogens here, so that third hydrogen is going to go on the first carbon. The hydroxyl, let's do this in yellow, the hydroxyl is going to go to the other one, which in this case is the second carbon. Here the rich get richer, so my final compound is going to look like this. So I've got my hydrogen, my extra hydrogen there, and my hydroxyl here. What is this called? This is now called pentane, but I've got this hydroxyl group here, which turns us into something called an alcohol. In order to create an alcohol, we take off the ending and we add OL. So this is actually called pentanol right now. And there's only one product in this reaction. Okay, so here's what's going on. There's our 2-methyl 1-pentene plus water. Here, I can either have the hydrogen bonding to the second carbon, which you see there, and the hydroxyl bonding to the first carbon, which you see here, or I can have the hydrogen bonding to the first carbon, which is there, and the hydroxyl bonding to the second carbon, which is there. This second product is my major product according to Markovnikov's rule, because this carbon already has 2 hydrogens, so the rich get richer and it gets more hydrogens. Okay, now we're going the opposite way, beginning with the appropriate alkene. What is the equation for the production of 2-chlorobutane? Whoops, so 2-chlorobutane is what I want to make. So when you're reading these, you need to figure out your question here. So 2-chlorobutane is what I want to make. So let's draw what this looks like. First of all, your parent chain is 4 carbons because of butane. There's all single bonds. And at carbon number 2, you've got a chlorine. So your question is, what is the alkane that we started off with? So this came from something. First of all, we know that because there's only 1 chlorine, it cannot be a halogenation. If it was a halogenation, I'd need to have 2 chlorines here because there's only 1 product. So this tells me that this has to be a hydrohalogenation instead. Okay. In a hydrohalogenation, you are taking a hydrogen with whatever your halogen happens to be. In this case, it's chlorine. So one of my reactants is going to be HCl. So now what's my other reactant? In order to create this, I needed to have a double bond somewhere. Now the double bond could be in any of these places. The double bond could have been here, or it could have been here, as long as it's by the chlorine. So I could have had one butene, or the double bond could have been here, and it could have been 2 butene. So which product makes more sense? According to Markovnikov's rule, that hydrogen probably went over here so that this carbon had more hydrogens and the rich get richer. In this case here, if the hydrogen was there, then I could have also had that, but our most likely candidate is most likely this one here. So I started with 1 butene and hydrogen chloride to produce 2-chlorobutane. Okay, so this is kind of what we did here. The double bond could have been in either of those places, so I could have had a number of potential reactants. 1 butene, I could have had 2 butene, and if you recall, when that double bond is somewhere in the middle of an alkene, we could have geometric isomers, where we can have the trans or the cis. Okay, so putting this together, there's my 2-chlorobutane, my hydrochloric acid, and then either of my reactants. We're not entirely sure which it is, so as long as you put one of them, you do not need to put all three. As long as one of them is there, that would make it correct. And there is a very, very funny joke. Okay, so that takes us to the end of our reactions for alkanes and alkenes and alkynes. One thing I do want to say is if this reaction was going through with an alkyne, we have to break apart one bond, so the alkyne would go to an alkene first, and then the alkene could go through another addition reaction to produce an alkane. It's a step-by-step process getting rid of one bond at a time.